You know that feeling, right? You look up into a clear night sky, lock onto a bright star, and just watch it. It doesn't just sit there. It shimmers, it pulses, it seems to dance. It's one of those beautiful, timeless things that has fascinated humanity forever.
But what's really going on? I mean, why does that tiny pinprick of light, after traveling for who knows how many years through the dead, silent vacuum of space, suddenly decide to put on a light show in the very last second before it hits your eye?
Well, here's the big secret. The spoiler alert is right there on the screen. The stars aren't twinkling at all. Seriously, they are, for the most part, incredibly stable, constant beacons of light. That whole beautiful flicker, it's all an illusion created right here at home.
So, if the stars aren't the ones doing the twinkling, what is? To figure this out, we're going to have to bust a myth that's been around for literally thousands of years. And believe me, people have been wondering about this for a long, long time. Way back in the 4th century BC, even Aristotle was like, hey, what's up with that? But he couldn't explain it. Fast forward to the 17th century, and some astronomers had this wild idea that stars were like giant spinning diamonds. It wasn't until the 20th century that we finally nailed down the real culprit. And it turns out the answer isn't millions of light years away in deep space. Nope, it's wrapped around our planet like a blanket. The entire reason stars twinkle is because of our own atmosphere. Of course, science has a fantastic, fancy name for this: stellar scintillation. It's just a precise way of saying that a star's brightness and even its color are changing really fast, all because its light is taking a very bumpy ride through the air to get to us. Okay, so let's walk through it. A perfectly straight, steady beam of starlight hits the top of our atmosphere. But our atmosphere isn't calm. It's full of swirling pockets of air, all at different temperatures and densities. Each one of these pockets acts like a tiny, wobbly lens that bends the light. So that straight beam gets bounced around, zigzagging all over the place. By the time it gets to your eye, it's that super fast zigzagging that your brain just sees as a twinkle. The absolute best way to picture this is to imagine you're looking at a coin on the bottom of a swimming pool. You know how the ripples on the water make the coin's image look like it's shimmering and jumping all over the place? It's the exact same idea. The atmosphere is the rippling water, and the star is the coin. And what's really wild is the scale of this. The atmosphere creates this shifting pattern of light and dark spots on the ground, and each little speckle is about 7 to 10 centimeters across. Now, your eye's pupil is way smaller than that, so as this pattern of speckles rushes past, your eye catches a bright spot, then a dark one, then bright, then dark, and that is the twinkle you see. It's your eye moving through the pattern. Okay, but this whole atmosphere explanation brings up a really big question, a kind of head-scratcher that's actually the key to this whole mystery, right? You've probably noticed this yourself. You can go out and spot Venus or Jupiter, and they just shine with this solid, steady light. So what's the deal? If the atmosphere is messing with starlight, why do the planets seem to get a free pass?
Well, it all comes down to one simple thing: apparent size. Stars are so ridiculously far away that to us, they're just single points of light. All their light travels down one super narrow path, which is easy for our atmosphere to knock around. But planets are much, much closer. They actually appear as tiny little disks, not points. So light is coming to us from all over that disk, traveling down thousands of different paths. And the wobble from one path gets canceled out by the wobble from another. All those different paths of light basically average each other out. It gives the planet a kind of immunity to the twinkling effect. There's just too much light coming from too wide an area for the atmosphere to distort the whole thing at once. And what you get is a nice, calm, steady glow. But wait, there's more. Because twinkling isn't just about brightness changing. If you look closely at some of the brightest stars, you'll see they flash different colors. That's because our atmosphere isn't just a lens, it's also a giant prism. So, just like a glass prism splits white light into a rainbow, the atmosphere does the same thing. It actually bends blue light a little bit more than it bends red light. This splits the starlight, and the different colors take slightly different paths to your eye. And since each path hits a different turbulent air pocket, you get a quick flash of red, then a flash of blue, then green. It's a beautiful little light show. And you can totally see this for yourself. The next clear night you get, go find the brightest star in the sky. That's serious. Because it's so bright, our eyes can really pick up on this color flashing. Some nights, it honestly looks like a tiny disco ball just flashing away. Now, where a star is in the sky makes a huge difference too.
If it's directly overhead, its light is cutting through the thinnest possible slice of atmosphere. But as a star gets closer to the horizon, its light has to travel sideways through way more air, sometimes 10 times as much or even more. And more air means more turbulence, which means way, way more twinkling.
So for us, twinkling is beautiful. But for an astronomer trying to get a sharp picture of a distant galaxy, it's a total nightmare. So how in the world do they fight the flicker?
Well, they have a few tricks up their sleeves. For one, a big telescope mirror is much wider than those atmospheric speckles we talked about, so it collects light from lots of speckles at once, which averages everything out and calms the image down. But of course, the ultimate solution is just to ditch the atmosphere entirely with a space telescope, like Hubble or the James Webb. Up there, there's zero twinkle. And for the telescopes that are stuck here on the ground, they use this incredible technology called adaptive optics. It is mind-blowing. They have a mirror that is literally flexible, and it changes its shape hundreds of times a second to perfectly counteract whatever the atmosphere is doing. It cancels out the twinkle in real time. It's just brilliant.
Okay, so we've established that twinkling is an illusion, we know the physics behind it, and we know how scientists fight it. But here's the final twist. What if this problem could actually be a useful scientific tool? Well, it turns out twinkling also happens out in deep space. Radio waves from super dense stars called pulsars also twinkle. It's not because of our atmosphere, though. It's because their signals are passing through giant invisible clouds of plasma drifting between the stars. It's the same effect, just on a galactic scale.
And by studying how those radio waves twinkle, astronomers can actually map out the invisible stuff between the stars in our galaxy. So the twinkle isn't just noise anymore, it's data. It's like a super high-res snapshot of what our air is doing, and at the same time, it's a map of the galaxy itself. So the next time you're outside on a clear night and you see that familiar little flicker in the sky, maybe you'll see it a bit differently. You're not just watching a star. You're watching the very end of an epic story, the story of a beam of light's chaotic, turbulent journey through our atmosphere to finally reach you. So what story is the universe trying to tell you?